Welcome back to the AutoML lecture series. Today we will talk about how to search in neural architecture search. So now that we have seen typical NAS search spaces, let's talk about the actual methods for solving NAS. So we have defined a search space. We also need a strategy to actually navigate it efficiently. Due to the fact that even a compact search space can contain thousands of valid architectures, making the search strategy very important. And the choice of search strategy directly impacts which architectures are found and how much compute is spent. Therefore, the key questions we want to answer in this part is, given a fixed evaluation budget, which search strategy finds the best performing architecture, and why does it outperform simply sampling at random? As already mentioned, we have seen typical NAS search spaces from cell-based to hierarchical search spaces, and now we actually want to do the search. And the goal of the search is to find the optimal architectures, and there are two different categories commonly used in NAS. Black box optimization techniques, which we have already seen in hyperparameter optimization, which we want to apply here for NAS, or one-shot techniques, which we will discuss later. So first of all, give you an overview about basic and black box optimization techniques. Basic algorithms can be, for example, random search or local search, whereas black box optimization techniques, as you have also already seen in hyperparameter optimization, can be Bayesian optimization or evolutionary algorithm. These are widely used due to their strong performance. However, they tend to use more computational resources than one-shot techniques. Black box optimization techniques, therefore, are kind of very simple, but often very expensive. However, they were used as the starting point when we want to talk about NAS methods, and we can combine them with different performance estimation strategies, which we will eventually also talk and discuss about later. So let's start with the basic algorithm, random search. Random search, as the name already suggests, just selects an architecture randomly from the search space and fully trains it. The architecture with the best score is then the output given a certain budget. And the budget can be, for example, the amount of compute you want to use, the time you want to use, or also the amount of different networks you want to evaluate. Random search is actually a very strong baseline in a constrained search space. And a constrained search space can be, for example, a search space which only has very similar performing neural networks. Local search is also a basic algorithm, where the idea is to iteratively train and evaluate all neighbors of the currently best found architecture so far. And the neighborhood is defined as all architectures that differ only by one operation or edge. And it's also a very strong baseline and based on a step-by-step neighborhood-based search. And we can mimic and we can view it as kind of a mimic of how we human would design a neural network. So if we found a neural network which works quite well and we want to adapt it to maybe check if the adaptation is better or worse, we just do very small locally changes. So changing an operation or an edge. And that is exactly what local search is also somehow doing, changing small locally, optimally changes, which are eventually made. And another approach which is very widely used also in hyperparameter optimization, or also especially here in neural architecture search, are evolutionary and genetic algorithms. The idea is here to iteratively update a population of architectures, and in each step, one or more parent architectures, which are mostly high-scoring architectures, are sampled, combined, and mutated to create new children architectures. And these children are then eventually trained and added to the population, replacing individuals with the worst scores. And there are several steps where the evolutionary algorithms actually differ by. One example could be the initial population sampling. So we could use trivial architectures, we could use random sampling or hand-picked high-scoring architectures, which we as humans think, yeah, they should be very good starting points. The second part is where methods can differ is the actual parent selection. So we could do a tournament selection, selecting best architectures out of a random population. We can do a random sampling weighted by the actual fitness of the networks. We could choose the currently best architectures as parents. And all these parts actually provide a trade-off between exploration and exploitation of the best regions we have found so far. And the third area where the methods can differ is the actual children generation. We have the mutation, where we want to combine two networks by adding or removing a layer, altering the hyperparameter of a layer, adding skip connections, or the crossover, which combines two networks. However, here in NAS, we have kind of the permutation problems. Since different graph encodings, we mostly look at neural architectures as graph, can represent equivalent networks. So one network can be represented by different graph encodings, and doing their crossover can eventually result in dysfunctional networks eventually. One approach which I want to mention here, which is very widely used, is the so-called regularized or aging evolution. It's actually kind of a standard evolutionary algorithm, with the difference that instead of the oldest solution, we drop the one. Instead of dropping the worst solution, we drop the oldest solution. So we kind of make sure, therefore, to keep exploring. Therefore, we are able to maintain the population diversity and prevent premature convergence. So in standard evolutionary algorithms, as I just mentioned, we rather drop the worst solution, since they are not being sampled as being parents for the next generation. So here, dropping the oldest gives the actual name of the algorithm, aging evolution. And the architectures that have been around for too long die off in order to make space for more exploration, as already mentioned. And this can be also seen as a type of regularization. Therefore, this explains the second name, regularized aging evolution. One example the paper from 2019 looked at is categorical hyperparameter space. Here on the example of a cell structure search space, we have 5 categorical hyperparameters. So we first of all choose for the 2 previous feature maps, which we can see here in the gray part. We have the choice between operations for these 2 feature maps, and we ask for what kind of merge we want to use for this operation. So either an add or concatenation. So we have 5 different hyperparameters which we want to adapt using categorical information, eventually leading to the overall cell, which we can see on the right-hand side. So first asking which is the feature map which comes into my operation, and how do I combine these operations with each other. Eventually, as I already mentioned, this evaluation simply tackles neural architecture search as a hyperparameter optimization for 2 times 5 variables, since we look at 2 different cells, the normal and reduction cell. And in regularized evolution, we drop the oldest instead of the worst. Therefore, it's quite a standard evolutionary algorithm with the novelty of dropping the oldest. And interestingly, in 2019, that approach achieved state-of-the-art performance on the ImageNet image classification task at the release time. And we can also interpret the decisions directly, which makes it even more interesting. So we have here the 2 examples. So at the top, we can see what happens if we change the hyperparameters, which influences the hidden state. So instead of having the hidden state coming from feature map number 3, the feature map comes from number 4. Instead of number 3, therefore, we remove an edge and add an edge, which already has a quite substantial impact. And if we, for example, change the hyperparameter for the operation, changing the operation changes the overall neural network. And for example, changing the operation from an average 3x3 pooling to a none completely removes the operation, leading to a complete different neural network. So therefore, this also has a quite substantial neural network, and we can directly see each result and their effect on the actual neural network. Another approach which we also use a lot in neural architecture search is Bayesian optimization, since it's a very powerful tool for optimizing expensive functions. Bayesian optimization, just like for a small recap, has 2 key components, a probabilistic surrogate and an acquisition function. And it's an iterative algorithm where we select an architecture, maximizing the acquisition function, we train the architecture, and then we retrain the surrogate. And the acquisition function with our most popular and thus are expected improvement and upper confidence bound. It's important to note here that Bayesian optimization with Gaussian processes and standard kernels, which are mostly competitive for low-dimensional continuous problems, are not that relevant here for neural architecture search, since neural architecture search has a very high dimensional space. However, if we encode architectures using, for example, categorical hyperparameters, tree-based methods were already a very good starting point already in 2013. So in 2013, The paper TPE used a joint optimization of a vision architecture using a combination of hyperparameters and architectural topologies, for example, the number of layers and the number of hidden units, to actually achieve state-of-the-art methods on 3 different tasks: face matching, face identification, as well as object recognition, and therefore showing that Bayesian optimization with tree-based method is already a very great success. Apart from that, in 2016, likewise using Bayesian optimization with a random forest in SMAC, jointly optimizing the architecture as well as the hyperparameter, yielded also new state-of-the-art results on the object recognition task of Cypher 10. So we're having image classification, 10 tasks, without using any kind of data augmentation, which eventually led to a system called AutoNet. So we can see here already before 2016, with the big hype of deep learning, Bayesian optimization with tree-based methods on NAS was very competitive, improving over human-designed networks. In 2018, first steps were made in similar to also regularized evolutions, encoding the architecture categorically, and creating a kernel for a broad range of different architectures. Another approaches use neural networks instead of Gaussian processes. So using, for example, graph-structured neural networks or different types of embedding instead of a Gaussian process eventually led to very strong results in Bayesian optimization in recent years. And in summary, what was the most important parts here of this video is that basic algorithms perform very well on highly engineered search spaces. So if we don't have a very large variety of different neural networks, random search and local search are very competitive, but they face issues as soon as we go to larger, diverse search spaces. Whereas black box optimizations are widely used to their very strong performance. They can be used in combination with hyperparameter optimization and architecture optimization jointly. They allow for an easy adaptation to new problems. And the good part is here we can even make them more efficient by combining them with different performance estimation strategies to even make them more competitive and less expensive. So thank you very much for listening. I hope to see you in the next video.